Yeah, thank you, everyone. Thank you for being here. Thank you for organizing this wonderful series and for giving me the time to talk about sediment-hosted zinc-lead deposits. These are georesources that are crucial, yeah, crucial for reaching a net zero CO2 emissions society by 2050. We really need to diversify our energy supply with larger contributions of solar, wind, and hydrogen. But at the same time, harvesting renewable energy requires a lot of resources. So we can think of zinc and copper in windmills. And this, in turn, will lead to an increase in the yearly demand for minerals for clean energy technology. However, the number of new discoveries of major base metal deposits globally has been few over the last decades, and most shallow deposits have been hard to find. Most shallow deposits have been found. So we must explore for metal deposits at greater depths, which is much harder to do. It's more expensive and it requires different techniques. So in order to meet the growing demand for minerals through exploration at greater depths, we need to understand a process chain from the pore scale to the deposit scale all the way up to like the regional, maybe the global scale and back, so that we can address the knowledge gaps in our conceptual models of resource systems. And what I present today is some numerical modeling work looking at part of this process chain going from regional lithospheric scale to sub-basin scale for a specific type of base metal deposit called clastic dominated type deposits. So for abbreviation, I'll just say CD type deposits. They are the largest source of zinc and lead globally, and they formed a very long time ago during the Proterozoic and the Paleozoic by saline fluids that circulate through the sedimentary basins in the rift systems. They scour metals from the source rock deeper in the basin and then bring it up along faults that focus the fluids, and then the deposits are deposited during or after post-rock formation. So rifting actually provides the components of the mineral system that we think are important. So there are high temperatures and high heat flows in rift systems that drive fluid flow and also increase the solubility of the metals. The rift shoulder erosion provides continental sediments to the system that can act as a source for the metals. The organic rich marine, reduced marine sediments, they can act as host. And then seawater evaporation leads to really like saline brines that have increased metal solubility. And then of course there are faults that can act as the fluid pathways. So we can sort of create a cooking recipe from these mineral system components that that we can use to analyze the numerical results. So what we need are the source rock, so warm, hot, clastic, permeable continental sediments. I will call them sandstones, and I will color them yellow if they're just sandstones. And if they're in the right temperature window, I make them dark green in the model results. Then we need the host rocks, so the reduced marine sediments with lower temperatures that can trap the metals. They will be light green colored if they're in the right temperature window. We also need the saline fluids. These we'll have to imagine in the results. And then the fluid conduits, they will be the faults, and they will be colored in grayscale. All right, so with the numerical models, we can then answer the question, which rifting conditions favored the formation of CD-type deposits? And the model setup that I use consists of a coupled model of a geodynamic simulation using the software aspect and a landscape evolution model called FastScape. And I then model 3 different rift types, and each of the rift types I use 9 initial plastic strain configurations, so just different configurations of tectonic inheritance, so to say. And since we're only interested in, well, mostly the basins, I'll just show you the upper 50 kilometers of the model. All right, so let's see how a narrow asymmetric rift evolves. We start off with this initial distributed faulting. Then we create some rift shoulder topography. And once we erode that, we can deposit those sediments into the created basin. So here we can see we have some sandstone or sands being deposited. Then over time, major faults localize. You can see here for the high strain rates. And along these border faults, we get significant sedimentary infill. Then the rift starts to migrate by 10 million years. We have a stenospheric upwelling that is heating the system from below. And you can also see that we have some host rock being deposited here. This is then in the next snapshot, this host rock is buried by some new continental sediments. But what we also see is that the bottom of the sedimentary pile in the narrow margin is creating source rock. And by 20 million years, we have the situation where we have, because of the rift migration, we have these synthetic faults coming in. So, and they're connecting the source rock and the host rock. And we think this is a potential mechanism for ore formation. And we call it mechanism 1. We'll come back to it a little bit later. But then with time, rift migration stops, the rift stabilizes, and we no longer have active faulting in the major basin. So there are no more ore formation scenarios in the major basin. Okay, just to zoom in a little bit on ore formation mechanism 1, we can see that for a specific period of time, we have these synthetic faults that provide a pathway from the source rock to the host rock. And I've drawn these white arrows to say like this would be the interpreted flow of the fluids carrying the metals. And then once they hit the host rock from below, this is where they would deposit. This is indicated by the stars. And then the time window for mineralization is constrained by the fault activity, basically. Now, in analyzing all the simulations, we came across 2 other mechanisms. So mechanism 2 is a scenario where the source and the host rock both form in the border basin, and it's actually the border fault that connects the 2, provides the focusing pathways. And here, the window for mineralization is constrained by the activity of the border fault, but as you can see, also by the burial of the host rock, moving it out of the temperature window. And then a final mechanism is where, again, we develop some source and host rock in the same basin along a border fault, but this border fault is no longer active. But it could still be reactivated, it could still be more permeable. So we say, okay, well, this is slightly less favorable, but let's still call it an ore formation mechanism 3. And then this is predominantly occurring in the wide margin. And then to summarize all the different simulations together, I took the averages of the number of basins with source rock, with source and host rock, with mechanism 3, and then with the most favorable mechanisms 1 and 2. And then to give an indication of the amount of metals that could be leached from the source rock, I plot the total source rock area. So here it's about 24.5 square kilometers. And you can see that if we look at the other rift types, that narrow symmetric rifts are a lot less favorable. There's hardly any ore formation mechanisms identified, and we only have like 1/3 of the source area. For wide rifts, there is that we can see some ore formation mechanisms. This is because the wide rifts also experience some rift migration, but again, the source rock area is only about 1/3. So this is again a less favorable rift type. And so we can answer our first question in saying that asymmetric rifting and continuous migration create the largest border basins with the largest source rock and the most ore forming events. All right. Now, interestingly, Hoggart et al. Found in 2020 that big deposits all lie close to steps in lithospheric thickness. So this is an example of Australia. You can see that all the circles, those are the CD deposits. They plot along the 170-kilometer LAB thickness isocontour. If you do a global analysis, then 90% of the metal mass is in this 200-kilometer corridor. So you can form smaller deposits, but the big ones, over 10 megatons, they're all within those 200 kilometers. So does that mean that rifting close to cratonic edges is favorable for CD-type metallogenesis? This I try to answer again with some simulations. So compared to the models before, I added in this thick cratonic lithosphere on the right. And this lithosphere is thicker, it's colder, it's stronger, as you can see over here. And then what I test is, again, the rift types and the strain configurations, but most importantly, the distance between this rift center and the edge of the craton. And then I'll just show you an example of a narrow asymmetric rift with a craton edge that's really close at 50 kilometers, because that contrasts nice with the previous example.
Anne, you have 3 minutes to go.
Perfect. And what you can see that we start off with this shear zone dipping towards the craton. It develops into this waterfall with significant sediment package. We start to accumulate some source rock here, but then we start migration. But we do not have this big waterfall on the right. It's only 7.5 million years later that we finally form this. And because that's close to the end of rift migration, we hardly form any source rock. I mean, there's a tiny little bit if you zoom in. And all the different plastic strain configuration simulations with a close craton, they migrate towards the right and they show this evolution. So our right border fault activity is delayed and we create less source rock. So just to summarize with the other craton distances, you can see that a close craton on average does not help in creating ore deposits in narrow asymmetric rifts. With increasing distance, we have more source rock area and more ore formation mechanisms. For wide rifts, the picture is a little bit different, where we have more source area and slightly more ore formation mechanisms, but they're spread out over multiple basins. So I would say that close rifting decreases the potential in narrow asymmetric rifts for ore formation, but it increases it slightly in wide rifts. But narrow asymmetric rifts away from cratons still concentrate source rock in one border basin and are the most favorable. So then that makes me think like cratons, they probably play a big role in focusing rifting, so in the mobile belts next to them, and maybe in preserving the deposits, but not necessarily in creating the right conditions for the formation of the deposits. All right, so just my 3 main takeaways of this talk. We will need more georesources, and geodynamic modeling can help us understand these resource systems. There is potential for zinc and lead ore formation in many rifting scenarios, but some scenarios are much more favorable than others, and this can help us narrow down the exploration space. And then narrow asymmetric rifts are the most promising rift type, and their potential can be reduced by rifting close to craton edges. So cratons probably play a role in preserving the deposits. Thank you.
Yeah, thank you very much, Anne, for an interesting presentation. Already there are questions, so we'll start with Cindy, and then we can go to Robert.
Thanks, Anne. It's great to have the world recognize how important rifts are to critical mineral deposits and their occurrences. And everything in your model is dependent on a seeded weak zone in the mantle. Where do you have any evidence from a rift zone world? And also then the fluids and you know, a lot of it depends on what you do with the mantle lithosphere thinning. Could you explain you know, what observations you have that support that kind of model and that fluid movement? And also that kind of extreme thinning without the production of melt, at least some small amount of partial melt that we those of us who look at geophysical data from rifts see degassing at craton edges, all even without a large manifestation at the surface. Those cratonic edges are causing upwelling, higher vertical velocities, and at least some melt production at the craton edges. Could you help us understand why you chose the kind of model that you have? That's
Yes.
the basis for your predictions.
Yes. So I think there are several components there that I could talk to. So I think part of it is the initial conditions where I prescribe thinning and initial plastic strain to localize deformation in the center. And this can represent any type of heterogeneity that we can expect. And we know that rifts often localize in old or orogenies or something. So there are these previous structures, inherited structures that can that help localize deformation and start rifting. And this is what we try to mimic with our initial conditions. And then in terms of fluids and melts, I'm not saying there are no melts. I do model like very slow spreading rifts, so they're not like the magma-rich systems. But I haven't looked at the melting component in these models, but there is. I'm not saying it's there, not there. I just haven't looked at that. And then for the deposits themselves, there are some deposits in Australia where they think they might be like a intrusion origin, like intrusion source for the metals, but that's like one example. And then fluids. I'm not modeling fluids in the system, so I don't do that here. But obviously they are very important. So I am working on using these snapshots from Aspect as input for a hydrothermal fluid flow code. And there I can actually model the fluids and how they pick up metals and transport, focus, and deposit them. So I think that we can say with more certainty, we can say how fluid patterns look.
So, sorry, just so that I understand, your basic premise is that the mantle, there's a crust to mantle weak zone everywhere in orogenic belts that enables that is the seed for a rift formation, is the basis for the stretching model, the mechanical stretching, correct?
We assume there's some tectonic inheritance
in the mantle,
in the crust and mantle lithosphere. Okay. That helps to localize deformation. Yes.
Okay, yeah, thank you for that, Robert Winch. A small one. Yeah, then the others, you can write them on the chat.
Yes, thank you for that interesting talk. You seem to apply your modeling to lead zinc deposits, but you've said very little about the chemistry of the source rock. And I wonder, isn't your modeling relevant to the collection of all kinds of trace elements and the precipitation to produce the lead zinc deposits might depend again on the chemistry of the rocks in which they precipitate. So isn't your model for the accumulation of trace elements really much broader than lead zinc?
Well, that would be great if it was. I think we can apply this framework to other systems as well. But as you say, a lot of it depends on the chemistry of the rocks and the fluids, which we do not include here. And for this, I again refer to the hydrothermal modeling that I'm doing right now, where we actually have saline fluids with like solubility, like metal solubilities that depend on the salinity and the temperature of the fluids, and then we can calculate where they pick up how many metals and deposit them where. But for true fluid rock interactions, that's a different project that we're actually coupling to a thermodynamic database that can actually really tell us how these interactions work. So this is a future work, basically.